if you're familiar with the multiplication rule from combinatorics, then you've already seen examples of permutations. But we've made it to the point where we kind of need a formal definition before we can continue moving forward. So a permutation is an ordered arrangement of the objects in a set. And a permutation with R elements is called an R permutation. Okay, so what does that mean? Well, let's look at an example. Suppose we start with a set made up of 4 people: Alice, Ben, Christy, and David. Some permutations of that set would be David, Christy, Ben, and Alice, David, Ben, Alice, and Christy, Christy, Ben, David, and Alice, and Alice, Ben, David, and Christy. And now the key thing that I want you to take away from these examples is that even though they all have the same 4 names in them, they're considered different permutations because the order of the names is different. All right, that's the key part of the definition of a permutation, is that order matters. Right? If the order doesn't matter, then it's something else. Then it's what we call a combination. And that's something that we'll be looking at in later lectures. Now, these 4 permutations here are examples of what would be called a 4 permutation, because each of them has 4 elements. Here, just a couple other examples. David, Christy, Alice would be a 3 permutation because it has 3 elements. And David, Christy would be a 2 permutation because it has 2. Now, counting the number of permutations of a group of objects is just an application of the multiplication rule. All right? So to see this and to kind of help us spot the pattern that's going to lead us to a general formula, I'm going to write out the permutations of some sets based on their size. I'm going to kind of organize them into this table here. A set with 1 element, there's only one way we can choose that 1 element, so the number of permutations of that set is going to be 1, which is equal to 1 factorial. Now, if we go up to a set with 2 elements, we can choose either of the 2 elements for the first position, and that leaves us with 1 choice for the second position. So the multiplication rule tells us that there are 2 times 1, or 2 possible arrangements, which is equal to 2 factorial. If we continue this, a set of 3 elements, there are 3 choices for the first position, 2 choices for the second, and 1 for the third, which gives us 3 times 2 times 1, or 3 factorial permutations. Now, if we continue this reasoning, we see that a set with 4 elements has 4 factorial permutations. A set with 5 elements has 5 factorial permutations. And at this point, you should be starting to see a pattern develop. The number of permutations of a set is equal to the factorial of its size. So that leads us to our first permutation formula, which says that if we have a set with n elements, then there are n factorial permutations of those elements. Now, that's a useful formula to have, but it makes the assumption that we want a permutation of the entire set. For example, our formula will tell us the number of ways that 10 people can be seated in a row of 10 chairs. But suppose we only have 7 chairs. What happens then? What happens when we want a permutation that's smaller than the total number of elements in the set? Well, once again, the multiplication rule is going to tell us what to do here with our example. The number of permutations is equal to 10 people that we can choose for the first chair, times 9 for the second chair, times 8 for the third chair, and so on out to 4 people left for the last chair in the row. If we multiply that out, we get 604,800 possible permutations of these people. Now, when I look at that 10 times 9 times 8 times 7, what I see there is the beginning of 10 factorial, but it's got the end missing, the 3 times 2 times 1. So suppose I start with this, with 10 times 9 times 8 times 7 times 6 times 5 times 4, and I multiply it by 3 times 2 times 1. Well, of course, now you know we can't just start arbitrarily multiplying by some random number, but if I multiply and divide by that number at the same time, That makes the expression into this thing we've got here, 10 times 9 times 8 out to 1 on the top, divided by 3 times 2 times 1. And now you should take a minute here and convince yourself that I didn't change the number. Okay, basically I multiplied the top and the bottom of this fraction here by 6. Okay, 3 times 2 times 1. Now, at this point, if I rewrite this using factorials, the expression becomes 10 factorial divided by 3 factorial. Okay, but now I want you to think about that 3 for a minute. All right, we started with 10 elements, 10 people, and we put them in groups of 7, the 7 chairs. But notice how 3 is equal to 10 minus 7. Now, it may seem a little awkward, but if we write the 3 factorial as 10 minus 7 factorial, then the equation becomes this. All right, now, why would we want to write it that way? Well, writing the 3 as 10 minus 7 means that now all of the numbers in the formula also appear in the original question. All right, so if we replace the number of elements in the set, that's the 10, with n, and if we replace the number of spots we have to fill, that's the 7 chairs, with r, we get a general formula for calculating the number of permutations of a set of n elements into permutations that have r elements. You can see that formula on the slide here. It's n factorial divided by n minus r factorial. Right? And you should refer this back to our question now. If in our question, n is equal to 10, the number of people, and r is equal to 7, the size of our permutations. And if you substitute those numbers into the formula, you should see that we do get the number that we calculated here, 10 factorial divided by 10 minus 7 factorial. You should also take a note of the last sentence there. We'll often write this permutation as NPR, where the N and R are subscripts. Okay, that's a very common notation that you'll see throughout combinatorics and throughout the rest of our lectures.